In this chapter, we are going to talk about sequential logic circuits. First, what is the sequential logic circuit? The sequential logic is a special type of circuit that has a series of inputs and outputs, and the special thing is the output of a sequential logic circuit depends not only on the present input values but also on the past outputs. So this effect has some form of memory. A sequential circuit is a combinational logic with additional properties of memory to remember past inputs. To that combination, feedback is also attached. And the clock signals are required for some sequential circuits, and this is the general form of a sequential logic circuit, and this is the part that combinational logic circuit is applied, and there is the input and there is the output. This output after this output is generated, it is stored in the memory, and this output also affect to the next operation. So in the next operation, the output will depend on its present input and also in the with the past output. So why we need some memory for a circuit? For example, if we take a decimal counter that counts numbers from 0 to 9, how we do that? First we get 0 and we add 1, and then we add 1 to 1, and the result will be 2. So then we add 1 to 2, and then the result will be 3, and we add 1 to 3. Likewise, we can add 1 and count 4, 5, 6, 7, 8, 9 like this. So through a circuit, if we have to do this, the circuit must remember the past output. This is a one operation and this is another operation. So the next operation must depend on the past output. So if we take this 1 to 1 is 2. So the next operation must add 1 to the previous output. So this 2 must be remembered. So for this kind of scenarios, we use sequential logic circuits. And there are two types of sequential logic circuits. And the first type is asynchronous circuits. This asynchronous sequential logic is not synchronized by a clock signal. They are operated through pulses. The output of the circuit changes directly in response to the changes in the input. The advantage of asynchronous logic is that it can be faster than synchronous logic because the circuit doesn't have to wait for a clock signal to process inputs. The speed of the device is potentially limited only by the propagation delays of the logic gates used. These asynchronous circuits use unclocked flip-flops and time-delayed memory elements. And however, this asynchronous logic is more difficult to design, and it occurs problems that not encountered in synchronous designs. The main problem is that digital memory elements are sensitive to the order that their input signals arise. If two signals arrive at a flip-flop all arrived at almost the same time, the state that the circuit goes into can depend on which signals gets to the gate first. Therefore, the circuit can go into wrong state instead of the expected state. The asynchronous sequential circuits are typically used only in few critical parts of synchronous systems where the speed is considered as a main requirement. And this asynchronous circuits used in parts of microprocessors and digital signal processing circuits. And the next type is synchronous circuits. Nearly all sequential logic circuits in today are clocked or synchronous logic circuits. In a synchronous circuit, there is an electronic oscillator called a clock. It generates a sequence of repetitive pulses called clock signals. That clock signal is distributed to all the memory elements in the circuit. The basic memory element in sequential logic is the flip-flop. Gate latches are also used in some instances. The output of each flip-flop only changes when triggered by the clock pulse. So the changes to the logic signals throughout the circuit all begin at the same time at regular intervals synchronized by the clock. Output of all the storage elements in the circuit at any given time, or the binary data they contain, is called the state of the circuit. The state of synchronous circuit only changes on the clock pulses. At each cycle, the next state is determined by the current state and the value of the input signals when the clock pulse occurs. And there are some advantages of synchronous circuits. The main advantage is synchronous logic is simple to design. And there are some disadvantages. Synchronous circuits are slower than asynchronous circuits. The reason is that the maximum possible clock rate is determined by the slowest logic path in the circuit, which also known as the critical path. The logical calculation from simplest to the most complex must complete in one clock cycle. So the logic paths that complete their calculation quickly are idle much of the time waiting for the next clock pulse. Therefore, the synchronous logics can be slower than asynchronous logics. And another disadvantage is synchronous circuits generate heat waste. The clock signals must be distributed to every memory container in the circuit, as this clock signal is usually high frequency signal. This distribution consumes comparatively large amount of power and consumes much heat. Even the memory containers like flip-flop that are doing nothing consumes a small amount of power, thereby generating waste heat in the chip. Now we are going to talk about a special type of logic circuit, and that is latch. And the latch is the basic storage element in a sequential logic circuit. And these latches have two stable states which are high and low. Due to this status, the latch is also referred to as bit-stable multivibrators. And I mentioned earlier that latch is a storage device and it holds the data using a feedback lane. The latch stores 1 bit until the device set to 1. The latch changes the stored data and constantly trials the inputs when the enable input is set to 1. There are different types of latches, which are SR latch, gated SR latch, D latch, gated D latch, JK latch and T latch. And let's talk about the SR latch and why it is this called as SR latch. Simply the S means set and the set state make output as 1 and R means reset and this reset state makes output 0. So we can simply design SR latch using NOR gates, and this is called as active high SR latch. It contains 2 NOR gates and there are 2 inputs R and S, which mean reset and set, and there are 2 outputs Q. This is the main output and this is the inversion of the output Q bar. So this output is connected to this NOR gate's input and the output of this NOR gate is connected to that NOR gate. And we can also design this SR latch using NAND gates and it is known as active low SR latch. Now we are in our simulator and now we are going to construct the SR latch. Here I am using NOR gates to construct this SR latch, and the SR latch that using NOR gates is called as active high SR latch. In this active high latch, both set and reset inputs are connected to the ground. So when the set input goes high, the output also goes high. And when the set input returns to low, however, the output remains high. The output of the active high latch stays high until the reset input goes high. So let's construct this SR latch. As we know, the SR latch has two inputs, which are reset and set. So let's get some inputs, two inputs. This is the first input and this is the second input. So I'm going to name them. I'm going to name this input as S, which this is the set input. So I am going to name this input as R because it is the reset input. And we are using here NOR gates, so there must be two NOR gates. And let's get these two NOR gates. And I place the first NOR gate in here. And I get another NOR gate and I place it here. So we know there are two outputs of this SR latch. Actually it is the output and the inversion of the output. So let's make those. So I'm going to name this as Q because it is the output. And I'm going to get another LED bulb and place it here. I'm going to name it as Q bar because this is the inversion of the output. So let's connect this circuit. The R input is, let's move this R input to up. Okay, the R input is connecting to this NOR gate and the set input is connecting to this NOR gate, and the output at the other input of this NOR gate will be the output of this below NOR gate. So let's connect it. Okay, the other input of this NOR gate will be the output of this above NOR gate. So let's connect it. Like this. So we can construct our SR latch. And let's check this latch. To do so, we have three cases to study. Let's take the first case. In the first case, we are setting S as 0 and R as 1. Let's see what happens. And S is 0, R is 1. So we can see the Q is equals to 0 and Q bar is 1. So let's write these things. Q is equal to 0 and Q bar is 1. And earlier I said that the SR latch has some form of memory. So if it has a memory, when we remove this R input, the output must remain the same because it remembers the previous output. So let's check it. We are giving 0 to R and we can see the output doesn't change. So it is true that this SR latch has some form of memory. So when the input is taken away, the output remains the same. So let's move to the next case. Now our second case is here. In the second case, we are set S as 1 and R as 0. S as 1 and R as 0. So in here, the output is 1 and inversion of this output is 0. The Q bar is 0. So let's check if we try to remove the S input. It doesn't change any thing in output. It remains the same. So these are the main cases, and actually these two cases are using in practical scenarios, and there is one special case that we have to study. Let's check what is it. This is the case 3 or the special case that we have to study. In this case, we are setting S as 1 and R as 1. The both inputs are 1. Let's see what happens. We have set the both inputs as 1. We can see the output. Both Q and Q bar is equals to 0. But can this happen? This Q bar means the inversion of Q. If the Q is equal to 0, the Q bar must be 1. But in here, Q and Q bar both are equal to 0. So this is against our laws. So we consider this case as a don't care case. So this case is not used in practical scenarios, and other cases when the S and R both are equal to 0. In this case 1, when the S and R both are equal to 0, the output is Q is equals to 1 and Q is equal to 0 and Q bar equals to 1. And in the case 2, when the both inputs are 0, the Q is equal to 1, Q bar equals to 0. So for the same input, there are two different outputs. So this state, the state which both inputs are 0, is called as the memory state. When the circuit comes to this state, it doesn't change any output. It keeps the previous output. So that is why this state is called as the memory state. So this is the SR latch, and also this SR latch can represent by using NAND gate, and it is known as active low SR